Hello, ideaXme listeners. This is Ana Guzman, Space Ambassador. I'm here this morning with Dr. Paul Abell, Chief Scientist for Small Body Exploration at Johnson Space Center in Houston, Texas. Hello, Paul. Thank you for joining us.
Good morning.
So, Paul, first off, who are you? Please give our listeners a little bit of your background and what you're doing here at NASA.
Okay, so my role at NASA, I'm the Chief Scientist for Small Body Exploration. What that means is I'm one of the key members who studies asteroids and comets. Those are the small bodies in the solar system. Specifically, my main area of interest is in the near-Earth asteroids. And I approach those from a scientific standpoint, an exploration standpoint, a resource standpoint, and a planetary defense standpoint.
So the question that everybody asks, what are the probabilities? What are the statistics showing as far as are we in danger? Will we have an impact?
Right. So it's a very good question, and it's a question that we get a lot, and especially I get a lot. We will get hit again. It's almost a certainty that we'll get hit. And our planet actually gets hit all the time by very small pieces, very small bodies. We have explosions in the upper atmosphere that are detected by our satellites looking down at Earth. But our atmosphere protects us from most of those things. So it's really the bigger small bodies, the bigger asteroids that we're worried about. What I want to stress right now is we have nothing incoming. We have nothing that's presenting a danger to the planet right now for the foreseeable future. But there's always that chance there's something that we haven't discovered yet that could come in and give us a bad day. So everybody knows about the dinosaurs, the extinction event 65 million years ago. We want to make sure that doesn't happen, and so that's one of the things that we concentrate on in terms of planetary defense. We had some recent events back in 2013, February 15th. There was an explosion in Russia. That was a 20-meter object, the Chelyabinsk event. We can talk more about that. But that was a relatively rare event. We don't get events like that happening too often. So, you know, that size range maybe once in 100 years, maybe once in 1,000 years in terms of statistics, but it's really hard to roll the dice, right? It's sort of like when you have a flood. You can have a 100-year flood, and then the next 2 years you have a 500-year flood, and then maybe you're not going to get a flood for tens, thousands of years. So it's a statistical sort of way of looking at it, but we really need to understand the population in total before we can have a different way of actually assessing the statistical likelihood of impact.
So when you talk about near-Earth objects, to give people an idea, how many miles out are you talking about?
So basically the near-Earth objects are things that come within 1/3 the distance between the Earth and the Sun. That's the sort of the distance. They come mainly from the main asteroid belt. So those are near-Earth asteroids. We get a few that come in from the Oort cloud and the Kuiper belt. Those are comets. They sometimes look like asteroids, but they're actually comets. So that's why we refer to them as near-Earth objects, because they can be asteroids and comets. The near-Earth object population is about 5 to 10% cometary, and the rest is 90 to 95% asteroidal. So these objects, when you have to classify a near-Earth object, it's about, like I said, 1/3 of an astronomical unit. One astronomical unit or sun distance is about 150 million kilometers. Of that number, there's some that come even closer, and those are the ones that we consider potentially hazardous, right? Mm-hmm. And so you're looking at things that come close to Earth, so much close that they actually get affected by Earth's gravitational field. And so those are the ones that actually present the hazard. So those are the ones that we concentrate on first. Even though we're aware of everything, we like to concentrate on the guys that may present a hazard in the future.
So going back to the original question of who are you? How did you come about getting here? In your childhood, were you dreaming about, working in space exploration?
Really good question, because I'm Canadian, and I grew up in a small town in Manitoba, Canada, about 120 miles due west of Winnipeg. The town is Wawanesa. It's 500 people. There's no lights. And of course, in the wintertime, the skies are very clear and dark. And so as a young boy, probably from the age of about 4 or 5 years old, I would lay outside and look up at the night sky. And I would see all the stars, all the constellations, the northern lights, the moon, meteors, satellites. And I was fascinated. In fact, There were many times when in the winter I would dress up in my snowsuit and lay outside, and my mother would have to check on me every 15 minutes to make sure I hadn't frozen to death. And I would just ask, another 15 minutes, mother, another 15 minutes. And anyway, so I was always fascinated with the night sky, and it was something that I was always drawn to. But it wasn't really until I think I got to university where I took an astronomy class, and I knew right from that moment, my first year in university, in my bachelor degree, that's what I wanted to do. I wanted to do something. I didn't know it was going to be related to near-Earth asteroids, but I knew it was going to be in that area. And then I started to do some things with, believe it or not, galactic astronomy and extragalactic astronomy. And while that was really interesting and intellectually very stimulating and rewarding, it didn't speak to me. And I really wanted to do something that would benefit humanity and something that I think I could achieve in my lifetime. In other words, seeing results of my work and testable within my lifetime. So I had to have something that was fairly close. And then I started to learn about asteroids. And I went to graduate school, and I learned about near-Earth asteroids specifically. And that was when I knew right away that's what I wanted to do. And I was very fortunate. So my PhD thesis project was all about identifying and characterizing potentially hazardous asteroids and their physical characteristics. And I was presenting at some conferences, and I actually got recruited by some NASA people here at Johnson 6 months before I finished my PhD. So I was very, very fortunate. I got my PhD in December of 2003, and I've been here at the Space Center since January of 2004.
So tell me about these missions you're working on, JAXA's
Hayabusa,
and NASA also has OSIRIS-REx that's
right.
heading over to Bennu right now.
Right. Yeah. So I'm affiliated with both of those missions. These are two sample return missions. So these are robotic spacecraft. The Hayabusa 2 mission, we'll talk about that one first. So Hayabusa 2 is a follow-on to the Hayabusa 1 mission, or just Hayabusa. Hayabusa means falcon, directly translated from Japanese to English. And it's the reason why they have it is the falcon is a bird of prey, and it actually snatches its prey in midair. So that's what the Hayabusa spacecraft did. It went to asteroid Itokawa, landed on the surface, touched down, grabbed a sample, obtained a sample, then came back to Earth. So that mission was successful, came back, landed in Australia in 2010. I was part of the recovery team for that. So Hayabusa 2 is doing something very similar, but it's a much more scientifically aggressive mission. They've applied the lessons learned from the original Hayabusa 1 mission, done some more advancement in terms of the technical capabilities of the spacecraft, the amount of sample they're going to get, and delivering payloads to the surface of the asteroid. So it's going to be really, really interesting. It's going to a carbonaceous asteroid, collecting a sample, and returning to Earth in December of 2020. And I'm on that mission to help out. The reason why they are interested in the carbonaceous asteroids are because they contain volatiles and organics. And so it's the water inside these asteroids. Some of these asteroids are maybe as 20% water by weight. And it's the water that is very, very scientifically interesting because that's very important for astrobiology, right? Understanding the organics in the water that is in these asteroids, getting that sample, we can learn a lot about the formation of the solar system, but more importantly, we can learn about how life on our planet and maybe other planets may have evolved, because there's this theory that a lot of the asteroidal material that has been delivered to the inner solar system has actually seeded planets, including our Earth, with material necessary for life to evolve. Mm-hmm. So that's one of the reasons, that's a main reason why they're going after this type of asteroid. Mm-hmm. The neat thing is, at the same time they're doing their mission, NASA's doing its own. So mm-hmm. JAXA, the Japanese exploration agency, and NASA are doing two separate missions, but they're going to happen almost identically at the same time. So we're actually having this really great synergy. We're able to cooperate. So OSIRIS-REx is going to Bennu. Hayabusa 2 is going to Ryugu. They're both similar asteroids. They're not identical. They're slightly different, but they're both carbonaceous objects. Both have organics and volatiles, we think, from our ground-based observations. Mm-hmm. And so it's a great opportunity for us to go out to these particular asteroids, learn about them, get sample, and come back. And we're actually going to exchange personnel and actually exchange samples. So we can actually leverage much more science capabilities than having our own mission standalone. So it's a great way of providing international cooperation and getting more out of these missions than we would normally do.
So the data that NASA and JAXA are obtaining from these asteroids, is it also going to help in trying to predict if they're dangerous to Earth, or in the event that there is another asteroid that might be dangerous to us?
Right.
You know how to get them out of the way, destroy them, maneuver them somewhere else?
Right.
What's the plan?
No, it's a great question. So one of the things about this mission, and one of the things I like about Near-Earth asteroids is no matter what type of mission you're doing when you send one to a near-Earth asteroid, it's not just a science mission, right? You get a lot of science, but it's also, you learn about the targets, like I said, about the water, right? So there's mining companies now on Earth who are very interested in resources that contained inside the asteroids. And asteroids are made of all sorts of different materials, and like I said, they're the carbonaceous ones, which are organic, volatile, rich, they contain water. But there's also ones that are metallic, and they contain lots of metals, precious metals like platinum, palladium, and things like that. And so it's actually the water and the precious metals that these mining companies are interested. Well, these science missions will be able to help determine those characteristics that will be of interest to mining. And then they're also interest to human exploration, because they're stepping stones as we move out into the solar system and maybe even get towards Mars and then beyond. So you can use them for that. And the water inside them, if you can extract the water, you can actually have supply depots waiting for you, because water is rocket propellant, right? You can divide water in hydrogen and oxygen. It's rocket propellant. It's also life support. Mm-hmm. And it's also radiation shielding. Water is a very good radiation shield. So one of the issues we have with deep space exploration is there's this radiation environment. We have to protect our crew members from this radiation environment for long duration. So maybe using that water maybe help. And then lastly, but by no means not important, it's really important, is we get to learn about these targets that are potential hazards and risks. Not to say that maybe Ryugu and Bennu, the targets of Hayabusa 2 and OSIRIS-REx, are direct hazards right now, but we get to learn about a population of objects that may present a hazard in the future. So knowing about their physical characteristics, knowing about how to interact with them, helps us understand and develop the techniques that we may need to use to deflect an asteroid in case when we see one heading our way.
So what is NASA projecting as far as when we would be able to have the technology or the type of vehicles that would be able to go to these asteroids and maneuver them somehow or affect their trajectory to steer them away from Earth's orbit?
Right.
And what's the reality, or what is the expectation?
So the expectation, so it's something we're working on right now. One of the things we have a NASA Planetary Defense Coordination Office, which is located at NASA headquarters. We are working and developing a couple missions. One is an early warning mission that we're in the process of development. It's got some funding. It's called NEOCAM, which stands for Near Earth Object Camera. And it's an infrared space telescope, and it will be placed between the Earth and the Sun and look and help identify these potentially hazardous asteroids coming our way, right? One of the things we have, I should state that we actually have a system of ground-based telescopes operating all the time as part of our network, our surveillance network. But they're only optimized, they're optical, so they use visible light that's reflected off the asteroids, and they're only good looking at nighttime. They can't see during the daytime, right? And so NEOCAM helps cover that blind spot of objects coming at us, from the sunward direction. It is also very sensitive at picking up very dark objects, which are harder for optical systems to see, right? So if you're just trying to look at an asteroid, you get the light that's reflected off the surface by the sun, right? They don't give off their own light. So if you have something that's big and bright and very close to you, that's easy to see. But things that are very dark, very small or smaller, and a little bit further away are much harder to detect with optical systems. However, in the infrared, because of the way the asteroids reflect and emit in the infrared, they're easier to pick up. So that's one system that we're working on. It's sort of a surveillance system in concert with our ground-based systems that are already operating. But we're also, which is really exciting, we're looking at developing, in collaboration with the European Space Agency, ESA, the AIDA mission, which stands for Asteroid Impact Deflection Assessment, AIDA. And it's a dual mission. ESA provides an observer spacecraft. We're going out to a Nearearth asteroid, which turns out to be binary. There's a primary asteroid with a smaller secondary that orbits around it. And then we provide the impactor. So what happens is ESA sends their spacecraft out to this binary asteroid. They characterize it, figure out everything they need to do to deal with it in terms of its scientific importance, also its any type of resources that may be there, but more importantly, characterize the system so that when we hit with our spacecraft, which is basically a big interceptor, big bullet if you'd like, they get to see what happens. So how much we actually deflect the asteroid, what actually physically happens to the asteroid. So it's a test of what we call the kinetic impact deflection technique. Kinetic impact because we're just ramming into an asteroid high speed with a spacecraft. And that's something that we're developing and hoping to test. So if we see something coming at us, we don't want to have to do everything right the very first time, right? There's a lot of pressure, and you have to have 100% success because bad things can happen. So it's like you always practice like you play. So you practice musical instruments before a symphony. You practice for sports. You have for the big game.
Right.
It's the same thing here. We're practicing how to defend the planet. So this is one of these missions that we're looking at.
That is fascinating. So on a personal level, how does it feel being part of a worldwide team that are essentially the Watchmen of Earth?
It feels pretty good. I love my job. I'm very passionate about the topic. There's a team. We have a team, so we're well coordinated, and it's not just the United States, not just NASA, right? We do have cooperation from other countries. The United Nations is involved as well in helping us with this particular type of threat. But NASA is basically taking the lead in this particular area. So it feels pretty good. I mean, we have a big responsibility, and it's exciting. It's sometimes a little intimidating if you think about it too much.
Right.
But it's actually neat. It's when you have a chance to save the world and make a big difference for humanity, and that's something we take very seriously. And we're on call pretty much 24/7, 365 days. So it's if it's not just me, there's like I said, it's a team, and there's always someone monitoring the asteroids when they're discovered, calculating the orbits, figuring out, hey, this one looks maybe a little bit more interesting, the other's interesting in the Chinese sense of the word interesting, that it may give us a bad day, so let's look at it a little bit more closely. And most of the time when that happens, we look and we find out, oh, okay, this object's going to miss. But occasionally there's certain objects that you have to work at a little bit harder to do. But it feels really, really good. It's an important role, and it's something that we take very seriously.
And for the parents or the students listening right now, obviously, if they were interested in going this route, you study geology, you study astrophysics and whatnot, but is there something along the way of your career that you learned that you didn't learn about in class or didn't know about in class?
Yeah, there are several things I learned by outside of class, I guess. And one of the things that I appreciated when I got to NASA was we never stop learning. I mean, that's the most important thing. I think anybody who's going into this type of field obviously has to have a good science background. But one of the things that we're finding, especially with near-Earth asteroids, because you combine geology with astronomy, there's also some engineering involved, science, things start to blur. It's not just one simple category. You can't just say, okay, I'm going to study chemistry only and then I'll know how to deal with asteroids. Or I'm only going to deal with geology, and I'll know how to deal with asteroids or understand asteroids. So it's really, really good to have a broad perspective. And I didn't think I appreciated that until I started getting into it in detail in grad school, and then even more so now at NASA, where we can bring in experts with all sorts of backgrounds and considerations. So, for planetary defense, you want to know a lot more about sort of the engineering, some of the physical properties, the scientific things, the geophysics, as we say with asteroids. For science, it may be different in terms of the basic geology, geochemistry, and things like that. And then there's the astrobiology, so you have the biology and chemistry as well to understand all these aspects of the asteroids, the near-Earth asteroids in particular. So it's that breadth of knowledge and being well-rounded and realizing that there's always something more to learn. One of the nice things about the type of work that we do, and we're going to see this guaranteed at Hayabusa 2 and OSIRIS-REx when they get to their asteroids, is we're going to be surprised, right? We think we have a pretty good idea until we get to the actual object. And this was a good example of this is if the listeners remember the comet Rosetta mission, right?
Right.
Going there, and all of a sudden they actually saw the comet nucleus, and it was completely different. And everybody, my colleagues at ESA, were all freaked out because this was like, oh my God, we had no idea it was going to look like a duck, right? and what do we do now? So we have the same type of experiences, and I guarantee you. So you always are prepared to learn. You're always surprised, and that's what makes it fun and interesting. So that's one major aspect I will tell. The other thing is, when you're on these types of missions, or when you're working for NASA doing this type of thing, you're not just a scientist, right? You're a scientist engineer, but you're also into public relations, right? You have to learn how to communicate well, not only with your colleagues and your teammates, but you have to be able to convey information to the general public. I work for the general public. Taxpayer dollars pay my salary. So if I can't get excited about my work, and I can't convey that excitement to the listeners and you and everybody else, then I'm not doing my job. So public outreach is a really, really big, important role that we have to play. And that's something that, when I first got hired on, I didn't realize was a part of my job that I needed to do. So that was another surprise. The other thing is, sometimes, especially when you work with international missions, you really get to learn about different cultures and different ways of doing things. So, for example, JAXA has a completely different approach to their missions than we do at NASA. And that is really refreshing to see, because we can make things much more robust. We can learn from each other. We can learn from our mistakes and also our successes, and apply that to make our missions much better in the future. So that's another aspect. And sometimes you're a diplomat, especially if you have to do these things. There's all sorts of things you have to be aware of. But that's what I love about my job. There's so many aspects. You're not just doing one thing. There's several things that happen all at once. So that's what I would say to the listeners.
So lastly, what are your plans for tomorrow? Because tomorrow is International or Worldwide Asteroid Day.
Right. So what's funny at NASA is we have the saying is every day is Asteroid Day for us, right? Because, it's great to have Asteroid Day, don't get me wrong. Asteroid Day is really important. It's good to raise awareness with the general public, but for us, every day is Asteroid Day, right? We have to watch the skies, we have to analyze orbits, we have to look at things, prepare spacecraft mission reports. And so what I'll be doing is a combination of things. I will be reviewing some papers. I'll be looking at data that's come down from our search telescopes and looking at potential asteroid targets, things that may be of interest from a planetary defense side, but also from human exploration side. So those are the things that I'll be doing. I'll also probably be talking to a few of the media outlets and explaining, exactly what I do and why asteroids are important from all standpoints, not only from planetary defense, but from the standpoint of science, from the standpoint of human exploration and resources as well.
Well, thank you so much, Paul, for taking the time to sit down with me and have our listeners take a broad look into what you do and what NASA and JAXA and other people in the world are doing as far as protecting humanity and studying asteroids and comets. We really appreciate it. and we look forward to seeing the results and the data flow in, and hopefully we can follow up with you next year and see what your findings are and how what the future holds.
Yeah, no worries. It was really my pleasure. I really appreciate it.
Thank you very much.
Thank you. Thank you.